Hey folks, welcome to chapter 10. We are going to spend a couple of lessons looking at waves. Talking about wave definitions to get us going. It's like, what are we looking at? What is a wave? We're not talking about waving at somebody or waving goodbye. Let me show you an animation actually about what a physics wave looks like, and then we'll see if we can turn it into words. So hopefully this is going to work. There we go. Let's get that out of there. So that's a wave. I want you to stare at that for a little bit and see if you can figure out what those blue dots are doing. Sorry, it's a bit laggy. It's actually kind of cool if you pick just one of the blue dots. Like look at maybe the blue dot sitting right along the y-axis here. You can see that those blue dots move up and down, but they don't actually move side to side. So it's pretty cool. A wave is a way that energy can be transmitted in one direction while the molecules themselves move in the opposite direction. So here you can see that the top of a wave is slowly moving to the right. And then the little blue balls, the little particles, are just moving up and down. Sometimes people think there's stuff going to the left, but there's nothing going to the left. And in fact, the little circles are not going to the right or the left, they're just going up and down. So that's kind of a neat little animation to stare at. Now, no big deal. We just have to put that into words. So here's what we're going to say. So what's a wave? It's an energy disturbance in a medium. There has to be something there for the wave to travel through. That's what we mean by medium. And it moves through both time and through position. So that time and position piece, I want to just focus on that for a moment. That means if you pick one of those blue dots and you stare at it as time goes by, the height has to vary. And that's true of this picture, right? If you pick one of those blue dots and you stare at it over time, its height is going to change. So that satisfies the requirement that heights vary with time. I believe I may have... There you go. That, hopefully we can see it, is not a wave because it doesn't satisfy that. If you pick any individual spot on the wave, like right there, and you stare at it for some amount of time, its height isn't changing. So this is a picture of a wave, but not a wave itself. We can also say at any one time, so if you do take a picture, then you have to have different heights at different positions. So if I go back to this screen, hopefully you can see that. That is also not a wave, because if you stop it at any point, if you take a picture of that, it would just be a flat line and you wouldn't have any heights that vary. So that one, it is changing through time. If you pick one spot and watch it over time, then that one spot is changing in height, so it satisfies that first requirement. But then if you pause it at any one time, it would fail the second requirement, which is to have various heights. So at any one time, heights have to vary with position. That you just gives us an idea where we're going with this chapter. So don't worry about regurgitating that on a test for me. Parts of a wave. Stuff we're going to talk about over the next 3, 4, 5 lessons. So we're going to sketch a little picture here of a wave. Might look kind of like a sine wave for those of you that are familiar with those in math class. Just talking about like the physical proportions of the wave. The amplitude of the wave is how far above or below the x-axis the wave extends. So we don't really want to call it the size of the wave because we're going to see that there's another way that we could measure a dimension of that wave. But amplitude is sort of how high or above the tops or the bottoms of the wave extend from 0, the x-axis. In terms of a sound wave, that would be like your volume. So the louder a sound wave, the larger the amplitude. Crests are any part of a wave that extend above the x-axis, and troughs are any part of a wave that extend below the x-axis. So this entire piece here is a crest, and this entire piece here we would call a trough. Just like what a horse eats out of. And crest, just like what you brush your teeth with? Toothpaste? Nah. Advertising at its finest. I'd mentioned that we don't want to call amplitude the size of the wave because there was another dimension. So you could measure how tall a wave is from the x-axis up to the top of a crest, or from the x-axis down to the bottom of a trough. In Physics 11, our waves will always be symmetrical that way, so the measurements are easy. Doesn't matter whether you measure x-axis up or x-axis down. But another measurement that's really important for us is the wavelength, which is how far side to side one crest and one trough are. And that's called a wavelength. And this symbol here is lambda. So maybe I'll sketch that in there. So that little symbol there is called lambda. And you don't have to put the fancy little feet on it. I always just do it like that, kind of like an upside down Y. And that is called the wavelength. So the wavelength is one complete crest, side to side, and one complete trough, side to side. Now with wavelength, with lambda, it's always measured in meters. You can measure from like here, from 0 on the x-axis through one whole crest, through one whole trough to there. That would be a wavelength. But you don't have to measure from there, right? You could still get a full crest and a full trough if you went from crest to crest. Because you've got half a crest, a full trough, and then half a crest. Or you could go from like a bottom of a trough to the bottom of another trough. So just keep in mind there are multiple places you could measure side to side in order to figure out what the figure out what the wavelength is. Waves also change through time. Remember we said they change through position, they change through time. You probably don't need to resketch this picture to be honest, but do remember that we haven't talked about this for a while. Period is the amount of time it takes for one cycle. In this case, period, which is a capital T, would be the amount of time for one complete wave to pass. So we're not really talking about like pendulum swinging or something like that. In your brain, maybe instead of thinking about period as being sort of one cycle, you want to think about that as the time for one complete wave to pass by. So a full wavelength, a full lambda. However many seconds it takes for that to go by, that's your period. So moving into a wave equation, we often like to talk about how fast waves move. Certainly for sound waves, certainly for water waves, there's all kinds of waves. We like to know how quickly they're moving. Velocity is measured in meters per second. And I want you to think about this. What did we just say has to be measured in meters? Well, that's wavelength. And what did we say about waves is measured in seconds? Well, that's period. So if you think about this equation, it simply becomes velocity equals lambda divided by period. You also will see, actually more commonly, this second version of the equation. So there's really two equations there. There's v equals lambda over t, or you can use v equals lambda times f. And it actually turns out that that's probably the more common equation that we use. That second equation is true because hopefully you remember from way, way, way back when, like in the very first chapter of this course. That's September, that's a long time ago. That frequency and period are reciprocals of each other. So 1 over the period is frequency. So that gives us maybe our more common version of the equation. But either equation works, it just depends on what they give you in a question. So let's try one here. Don't feel like you need to write that word for word. Like instead of saying find the frequency, don't write all that. Just say find f of some waves. Doesn't matter that they're water waves. If v equals 1.3 meters per second and wavelength, you could even put your little lambda symbol, equals 3.9 meters. You can speed things along for yourself there. In this case, we don't want to use the equation that involves period because they're asking us to find frequency. So this is as easy as plugging some numbers in there. V equals lambda times F. We get a frequency of 0.333 hertz. Remember, those are the units on frequency. Units for period were seconds. Now, I want you to think about what that means a little bit. I want this to be more than just calculations. So a frequency of 0.333 hertz means that you are getting 1/3 of a wave per second. So I want you to see if you can always sort of wrap your head around that. Just understand these calculations a little bit deeper. So that's 1/3 of a wave, 0.333 of a wave goes by per second. Just so you can picture sort of how quickly these waves are moving. Not terribly quickly. Let's try another question. We've got waves in a lake traveling 28 meters in 7.5 seconds. The distance from a crest to an adjacent trough, so adjacent just means beside, so from a crest to a trough is 60 centimeters. Ugh, centimeters, yuck. And how many waves pass one point in the lake every 2 minutes? Yeah, 2 minutes, that's kind of gross as well. Really, we're looking here for the number of waves passing a point every 2 minutes. So what we can do is if we take that last statement and we say to ourselves, hey, if we're trying to figure out how many pass every 2 minutes, let's get frequency or period. Either one of those. If we can somehow solve for a frequency or a period, then we'll be able to figure out how many of those waves go by in 2 minutes, 120 seconds. So, I don't know, let's go for frequency. Just for fun. V equals lambda times F. Turns out you actually don't have V and you don't have lambda. Not quite yet anyways. But we can find them pretty quick. Remember, velocity is meters per second. And here, this told us that the waves travel 28 meters in 7.5 seconds. So let's take that information and let's turn that into a velocity. Meters over seconds. Maybe I'll color code this a little bit for you. So let's take those down. V equals 28 over 7.5 equals 3.7333 meters per second. So that value is going to go in as V. And I'll use the answer button when I get there on my calculator. Now, the other thing we're going to have to figure out is wavelength. To get your wavelength, let's sketch a little picture. It's telling you, there's a terribly drawn wave, sorry. It is telling you that from a crest to a trough, so from there to there is 60 centimeters. But we have to think, is that a full wavelength? The answer is no. A full wavelength is a full crest and a full trough. You'd actually have to go to there. So you'd have to tack on another 60 centimeters, which would give you a wavelength of 120 centimeters. And then we don't like centimeters, right? We like meters. So we're going to plug that in as 1.2 meters. And that's going to let us solve for frequency. Let's try that on the calculator. It'll be that 3.7333 divided by 1.2. 3.111. And that's going to be hertz is your frequency. Now that's not really the final answer. The final answer was how many waves pass one point every 2 minutes. Let's not even do the 2 minutes, right? We don't like that. 2 minutes is 120 seconds. Now there's an equation you can use, or you can think your way through this. That 3.11 hertz tells you that there is just over 3 waves passing per second. And we want to know then how many pass in 120 seconds. So hopefully you're sort of sitting there going, oh, I think we could just multiply the two together. And you're exactly right. Don't forget, if you prefer equations, if you go to the top left-hand corner of your formula sheet, you'll find this equation. Frequency is number of cycles, in this case number of waves, divided by time. So you could think your way through it, or you could just go to your formula sheet and you could say, hey, I'm looking for the number of waves. The time's 120 seconds. Mathematically, they're going to multiply. 3111 times 120. 373 waves. So there's your final answer on that one. Maybe you're sitting there bobbing in the lake in a boat, and you have a little curse of the physicist moment. You're sitting there. There's going to be 373 little waves that pass by your location in 2 minutes. Moving on. Scroll, scroll, scroll. Sorry for that. Sure, let's try this. There we go. What about wave velocity in springs and strings? So any musicians in the room, this example's for you, or this knowledge is for you. It turns out that the velocity for a spring or string, sorry, I should say musicians, this would be like pianos, guitars, any stringed instrument, right? Not going to work for like saxophones or trumpets or clarinets, but anything with strings. The velocity that the waves travel in those stringed instruments doesn't depend on the amplitude of the pulse. When you go up to a guitar and you pluck the string, it doesn't matter whether you pluck it hard or soft, it's going to play the same note. The amplitude is simply the volume of the wave, or the volume of the note that you play. But how do you change the note on a stringed instrument? Well, you can change the tension. So more tension makes the waves go faster. Or you can change the density of the string. You can make thicker strings versus thinner strings. And more density slows thicker strings, slows those waves down. The equation looks like this. Velocity is equal to the square root of tension. And I know there's another capital T that's kind of confusing because we just talked about capital T as period. But I'm not going to mix a period question into a question like this for you. I'll try to keep them, or I will keep them both separate. It's tension divided by, or root tension divided by mass per meter. So you have to take your mass in kilograms and then divide by meters. So that little calculation on the bottom is your kilograms divided by meters, which we call mu, which looks like the coefficient of friction. So this is kind of confusing, this equation, just based on what we've seen previously in the course. But again, I'm not going to give you a friction question when we're looking at how fast waves are going in a piano. So don't sweat that. So that's tension. Remember, tension is measured in newtons. It's a force. And then this little mu value is your kilograms per meter. So let's try an example out looking at how fast waves might travel in a guitar string. Oh, sorry, and I should throw this in there. If the tension increases by a factor of 49, if you grab the guitar and tune the thing to make a string 49 times tighter than it was originally, and the thing didn't snap, remember you take the square root of something that got 49 times bigger, so the velocity would actually increase, not also by a factor of 49, but the square root of 49. You'd have a 7 times faster wave in that string. So let's try this. Guitar string has a mass of 1.48 grams. Mr. Akiri helped us there. That's okay, he's trying. And a length of 74 centimeters. We measured with a meter stick, which is actually usually measured in centimeters. Kind of counterintuitive. We're going to want to catch those. It says determine the tension necessary for a wave with a frequency of 440 hertz, which is an A that a lot of guitars tune off of. If it has a wavelength of 50 centimeters. Units all over the place. So here's what you want to do in this question. Let's use V equals lambda times F to figure out the frequency. and then we can go from frequency into maybe some tension. So the first thing we might want to do is figure out, using 440 hertz, that's a frequency. We've got a wavelength of 50 centimeters. Gotta watch those units. Let's see if we can't turn that into a velocity. So the wavelength, 50 centimeters, is half a meter times 440. Means in this guitar string, it is a guitar string, we have waves traveling at 220 meters per second. We also have to find that mu value in the equation, which is actually mass in kilograms divided by length in meters. So if we go and grab the 1.48 grams, convert it into kilograms, and we grab the 74 centimeters and convert that into meters, plug those values in, 0.00148 kilograms divided by 1,000, but the 74 divided by 100, 0.74 meters, we get 0.002 kilograms per meter. And now we can take that velocity, we can take that density, we can plug those into the equation. 220 equals root t over 0.002. You would want to square both sides. That gets rid of your square root. Oh, look, I've got it in there. Good. So there's the value. Multiply both sides by 0.002. We get a tension of 96.8 newtons. Two types of waves. Don't write this page down. Do not copy this page. Just listen really quick. I'll buzz through it. This video is probably getting kind of long. There are two types of waves. You might have learned about these if you've looked at earthquakes. So don't copy this. Longitudinal waves are in a push-pull motion. They were called P waves if you've looked at earthquakes. So a P wave is like a compression wave. It's actually moving this way down the substance. So it's like grabbing a slinky, stretching it out between two people, and you send a little pulse just sideways down the thing. That's a longitudinal wave. It travels along the compression travels along the direction that it's moving. So the disturbance is side to side, and the velocity is also side to side. A transverse wave is the kind we sort of think of when we're looking at waves, where if the velocity of the wave is moving to the right, then the little particles are actually moving up and down. So a side-to-side motion, they're a little bit slower. They were called S waves, or secondary waves, if you've learned about these in earthquakes. And that's like grabbing a slinky and not sending a little compression down the slinky, but grabbing the slinky and just like whipping it up or down. And you get that sort of snake-like pattern. So just to show you the difference between the two, you don't need to memorize those. There you go, disturbance up and down, but the velocity of the wave travels to the side. Actually, hopefully you can see what I'm seeing right now. This is just that little animation file showing you a longitudinal wave. You can see it sort of stretches and compresses along the line of velocity, as opposed to the one we saw earlier. There's your transverse wave, where the little circles move up and down, but the wave itself moves side to side. Phase, you can talk about whether waves are synchronized. So let me just put all three pictures. You don't have to copy this one either. So just listen. Do not copy. Save you some time. Waves that are in phase means that they'd be moving with the same velocity. Or maybe I shouldn't say that. Waves that are in phase means their crests match up and their troughs match up. So you can see in this top picture, I've actually drawn them slightly out of phase, so you can tell that there's two of them. But a crest is matching with a crest, and a trough is matching with a trough. If this is something like two sound waves that are in phase, what happens is the crests would actually add together and the troughs would add together, and you'd get these big amplitude crests and troughs, so it would actually be really loud. two waves that are slightly out of phase. If one of these waves is traveling a little bit faster, like maybe the orange one's a little bit quicker and it starts to pull ahead, now we've got these waves that are like kind of in phase but kind of out of phase, where the crests sort of match up but not perfectly, and the troughs sort of match up but not perfectly. And then you get to this stage down at the bottom where if we watch this thing for longer, maybe that orange wave like totally pulls ahead, and now a crest is actually matching up really nicely with a trough. The cool thing about the completely out of phase, we said in phase would be loud because the crests and the troughs add up. Here, if a crest and a trough are opposite each other, they're totally out of phase, then they actually cancel each other out. And this would be completely quiet. So this would be really loud when sound waves add up, and this would be like totally silent, where the sound waves cancel out. And if you have noise canceling headphones, I don't own a pair, but apparently they're great for people who like fly on airplanes. If there's a constant drone in the background, like the drone of an airplane engine, what those headphones do is they have a little microphone that picks up on that frequency, and then it emits a frequency that's exactly the same but out of phase. And the cool thing about emitting a sound that's out of phase to a background noise is it totally cancels it out. It makes it silent. Wouldn't work really well when people are talking, because the headphones are always playing catch up, and when you talk the frequencies are all over the place, and you'd always be sending out waves that are different and lagging behind. But anything a constant noise like lawnmowers, the drone of an airplane engine, apparently those headphones can cancel that noise out really, really well. That's different than noise isolating headphones, which are typically the big earmuff style ones. Those ones are just putting a nice big pillow on your ears to physically block outside noise from ruining your music. Here's the last thing for today, principle of superposition. This is kind of cool. When waves meet each other, whether or not they hit head on or one wave catches another, they pass through each other, so they don't permanently change each other, but their amplitudes briefly add together when they do spend that time meeting. So for example, if we take this little crest and a big crest and they move towards each other, they have sort of a head-on collision, what's going to happen is when they meet, their amplitudes add together through this thing called the principle of superposition, which is maybe what you've experienced if somebody's ever taking you tubing out behind a boat on the lake. Typically, boats will spin in 360-degree circles. You send waves out in all directions, and then the driver of the boat will look to see where those waves are adding up with other waves in the lake already, and then they go and they try to kill you on the tube. It's at least what my uncle does when he comes to the Okanagan every summer. Hey, let's put Josh on the tube. Let's go make some giant waves with principle of superposition, and then launch Josh off of those waves. I end up ragdolling. My kids think it's hilarious. Myself, not so much, but hey, the things we do for our kids. So the amplitudes add briefly together. And now the cool thing is these waves are just going to keep on going. This is kind of like the little handshake in the middle. After the fact, the waves keep on going as if nothing had ever happened. So I don't know about you, but I would almost expect that if the waves added together, then maybe the amplitude would be split 50-50 after the fact. But it isn't. They add together and then they keep on rolling at their original size until they go and meet another wave. So that's kind of cool. And let me show you in that animation file if this works, just to finish it off. Here's superposition. Let's see if I can dial this in. Hopefully you can see that. There's two crests meeting. Ooh, they make a nice big crest, right? The crests add together. But what if a crest and a trough meet? This looks kind of cool too. There you go. They do some kind of cool little meet semi-cancel thing in the middle. Little switcheroo. Here's the adding to make a nice big wave. That's how rogue waves form in the ocean. And then I'll show you one more where they're going to sort of cancel out partially. There you go. They keep on rolling as if they've never met. So that is your lesson on waves. Try the homework out from box number 1. If you have any questions about this material or about the homework, hit me up on Zoom or fire me an email. All of the documents you need for this chapter will be in the All Resources folder called Chapter 10 something. have fun, and we'll chat with you very soon on Zoom.